We live in a world driven by electronics. From smartphones to cars, electronic devices are integral to our lives. But what makes these devices tick? One unsung hero is the reset circuitry. Imagine turning on your computer, only to be met with a frozen screen. Frustrating, right? This is where reset circuitry comes into play. It acts like a safety net, bringing your device back to its initial state when things go awry. Whether it's a power fluctuation or a software glitch, reset circuitry ensures a reliable startup. So buckle up and get ready to master the art of reset circuitry design. Before diving into reset circuitry design, let's understand its importance. Reset circuitry forces a device into a known initial state, ensuring all components are initialized to their default values. Electronic devices are complex systems with numerous interconnected components. When power is first applied, these components might be in an unknown state, leading to erratic behavior. Reset circuitry ensures all components start from a stable state, preventing errors or damage. It also acts as a safety mechanism during operation, bringing the system back to a stable state if needed. Designing effective reset circuitry is crucial for any electronic device. Without a reliable reset mechanism, devices can malfunction, leading to system crashes or unexpected behavior. This is why understanding and implementing a well-thought-out reset circuit is essential for engineers and designers. Let's break down the design process into logical steps, ensuring that each phase is meticulously planned and executed. This methodical approach will help in creating a robust and efficient reset circuit. Step 1. Determine reset source. This is the foundation of your reset circuit design. Identify the source that will trigger the reset signal, such as power on reset, manual reset buttons, or watchdog timers. Each source has its own unique characteristics and applications, so it's important to choose the one that best fits your device's needs. Step 2. Select reset circuit type. This involves deciding between active low and active high reset circuits. Choose between active low and active high reset circuits based on your device's requirements. Active low circuits are triggered by a low voltage, while active high circuits are triggered by a high voltage. Understanding the behavior of your device will guide this decision. Step 3. Choose reset circuit components. This step is crucial for the reliability of your reset circuit. Select components like a basic RC circuit or dedicated reset ICs for more robust reset generation. RC circuits are simple and cost-effective, while dedicated reset ICs offer more precision and reliability. Step 4. Design the reset signal path. This involves planning the route the reset signal will take on the PCB. Ensure the reset signal reaches all necessary components reliably. A well-designed path minimizes the risk of signal loss or interference. Minimize the length and complexity of the reset signal path to reduce noise and signal degradation. This is critical for maintaining the integrity of the reset signal. By following these steps, you can design reset circuitry that guarantees reliable operation. Each step builds on the previous one, ensuring a comprehensive and effective design. Let's move on to explore different types of reset ICs. These components are vital for creating a dependable reset mechanism, and understanding their differences will help you make the best choice for your design. In reset circuitry, one size doesn't fit all. Each application has unique requirements that dictate the type of reset IC you should use. Understanding these requirements is crucial for ensuring the reliability and stability of your system. The type of reset IC you choose depends on your application's needs. Whether it's a push-button reset, a watchdog timer, or a power supply monitor, each serves a specific purpose. Let's delve into the details of each type. Push-button reset. ICs work with manual reset switches and include debouncing circuitry. This debouncing is essential to prevent multiple resets from a single press, ensuring a clean and reliable reset signal. Watchdog timer reset. ICs monitor the system for malfunctions and generate a reset signal if needed. They are critical in applications where continuous operation is vital, as they can automatically reset the system if it becomes unresponsive. Power supply monitor reset. ICs generate a reset signal if the voltage drops below a certain threshold. This is particularly important in systems where stable power is crucial, as it prevents malfunction due to power supply issues. Choosing the right IC involves considering your application's requirements. You need to evaluate the specific conditions under which your system operates and select an IC that can handle those conditions effectively. Factors include the type of reset source, reset threshold voltage, and package type. Each of these factors can significantly impact the performance and reliability of your system. Consult datasheets to compare features and choose the best fit. Datasheets provide detailed information on the capabilities and limitations of each IC, helping you make an informed decision. Now let's discuss calculating the reset signal duration. The duration of the reset signal is a critical parameter that ensures the system initializes correctly. Timing is everything in reset circuitry. The timing of the reset pulse must be carefully calculated to match the needs of your system. The reset pulse width ensures proper system initialization. If the pulse is too short, the system may not reset correctly. If it's too long, it could cause unnecessary delays. Let's see how to determine the optimal reset pulse width. By analyzing the system's requirements and using tools like oscilloscopes, you can fine-tune the reset pulse to ensure optimal performance. Timing is crucial in reset circuitry. The reset pulse width ensures proper system initialization. If the reset signal is too short, the system may not reset fully. If it's too long, it can delay startup. Determine the optimal reset pulse width from component datasheets. Consider the component with the longest reset requirement. Add a safety margin to account for variations and unforeseen factors. A typical safety margin is 10 to 20% of the calculated reset pulse width. Now let's move on to PCB design for reset circuitry. PCB design for reset circuitry is about ensuring the reset signal remains clean and strong. Keep signal traces short and direct to minimize noise and interference. Avoid routing reset signal traces near high-speed signals or noisy components. Use ground planes to reduce noise and crosstalk. Place decoupling capacitors close to the power supply pins of the reset IC. A 100 nanofarad ceramic capacitor in parallel with a 10 microfarad electrolytic capacitor works well. By following these guidelines, you can ensure a clean and effective reset signal. Next, let's discuss testing and debugging reset circuitry. Thorough testing ensures your reset circuitry behaves as intended. Let's see how to test and debug your design. Testing and debugging reset circuitry is crucial for a smooth startup. This process ensures that your device powers up correctly and operates reliably. Without proper testing, you might encounter unexpected behavior or system failures, which can be costly and time-consuming to fix. The power-up test. Connect your device to the power supply and observe the reset signal. This initial test is fundamental, as it verifies that the reset circuitry is functioning as intended right from the start. Pay close attention to the behavior of the reset signal during this phase. Use an oscilloscope to monitor the voltage level during power-up. The oscilloscope will help you visualize the reset signal and ensure it transitions correctly. Look for any irregularities in the voltage levels that might indicate a problem. The reset signal should transition to its inactive state after the designated reset pulse width. This transition is critical for the proper initialization of your device. If the reset signal does not behave as expected, it could lead to startup issues. The manual reset test. Press the manual reset button and observe the reset signal. This test simulates a manual intervention and helps verify that the reset circuitry responds correctly to user input. Ensure the reset signal behaves consistently each time the button is pressed. Ensure the reset signal duration meets the requirements specified in the datasheets. Datasheets provide crucial information about the expected behavior of components. Cross-referencing your observations with the datasheet specifications can help identify any discrepancies. The watchdog timer test. Simulate a system hang and observe the watchdog timer generating a reset signal. This test ensures that the watchdog timer can detect system hangs and trigger a reset, which is vital for maintaining system stability. Debugging tips. Double-check your circuit design, component values, and PCB layout. Small errors in design or component selection can lead to significant issues. Reviewing your work thoroughly can help catch mistakes early. Use an oscilloscope to trace the reset signal and identify any abnormalities. The oscilloscope is an invaluable tool for diagnosing issues in the reset circuitry. By tracing the signal, you can pinpoint where things might be going wrong. Now, let's discuss common pitfalls and troubleshooting tips. Understanding common issues and how to address them can save you a lot of time and effort. Collaborating with colleagues and sharing insights can also lead to more effective problem solving. Even with careful design, reset circuitry can have issues. Pitfall 1. Improper reset pulse width. Double-check the minimum reset pulse width requirements in data sheets. Use an oscilloscope to measure the actual reset pulse width. Adjust timing components or IC settings if needed. Pitfall 2. Noise and interference on the reset signal. Minimize noise by keeping reset signal traces short and direct. Use ground planes and decoupling capacitors to reduce noise. Pitfall 3. Improper grounding. Use a single-point grounding scheme to avoid ground loops. In electronics, reset circuitry is a silent guardian ensuring flawless operation. From simple RC circuits to sophisticated reset ICs, we've explored various reset solutions. Designing robust reset circuitry is an investment in your device's reliability and longevity. By understanding principles, best practices, and potential pitfalls, you can ensure smooth startups and reliable performance. Thank you for joining us on this journey to master reset circuitry design.